All right, here we go, video 8.2. We're going to do some more conservation of energy. Really, the only difference here is that we're going to be dealing with springs. All right, so remember, force exerted by a spring is responsible for elastic potential energy. And so springs always exert a conservative force. So we're still going to have our total energy staying constant, just like we were on the last one. All right, so what we've got here, this first example, let me begin this here. Let's see. All right, so Wile E. Coyote's got a mass of 20 kilograms. He's going to use the slingshot here to catch the Roadrunner. We're going to just treat the slingshot as a single spring with a spring constant of 120 newtons per meter, and we'll assume that the spring is, relaxed up here at the top of the slingshot to keep things simple. All right, it says he stands at rest at the bottom of the slingshot as shown here in the picture before he lifts his feet up to be launched. All right. So the idea is that I need to switch pages here. Sorry. So the idea is we're going to call this right here, we're going to call that point A. All right. And so the idea is at point A, let's call that a height of 0. So his GPE is going to be 0. He's clearly not moving there, so his velocity is 0, which means his kinetic energy is 0. So the only type of energy he's got there is elastic potential energy. And based on the drawing, it looks like the spring, the rubber band, is stretched 8 meters. So we can calculate our EPE. It's going to be 1/2 K, which is 120 newtons per meter, times X. Don't forget to square it. And that gives you 3,840 joules of energy. All right, so at point A, there's our total energy, 3,840 joules. All right. So then he picks up his feet. The first question wants us to find his velocity when he gets up to here, as he, gets released from the slingshot. All right. So let's call that point B. So the idea then is at point B, the height is no longer 0, right? And in fact, he's moved up, as the drawing shows, 4 meters. So we can find our GPE just by doing his mass times 9.8 times the height, which is 4 meters. So that gives you 784 joules worth of energy. At that point, the slingshot is no longer stretched, so our elastic potential energy is 0. And since the only forces acting on him from point A to point B are gravity and the spring, the total energy has to be the same. And as a result, our kinetic energy must fill in the gap, right? So 784 plus what is 3840. So the kinetic energy turns out to be 3,056 joules, which you can then use to find your velocity just by using this guy. And you end up getting 17.5 meters a second. All right. So that is the velocity there. Okay. Then part B says, how high will he be at his highest point? Okay, well, let's see. So here's what we know. At B, we know the velocity is 17.5 meters a second. We know that his total energy is 3840. And we know that this initial velocity is at an angle of, well, let's see. Let's clean up the board a little bit here since I've kind of written down what I need from this. So let's clean this up. So when he goes off of the slingshot, he's going this way, right? So I'm going to, for simplicity, just assume that the angle he gets launched at is this angle right there. So you can see there's a right triangle here. It looks like this opposite side is half of my hypotenuse. This must be a 30, 60, 90 triangle. So at the top of his path, his velocity is just Vx, right? So that's 17.5 meters a second times the cosine of 30 degrees, right? Just doing some vectors here, right? When he gets to the top of that path, remember the horizontal velocity stays constant, or vertical velocity is 0 at the top. Okay, so the velocity at the top ends up being 15.14 meters a second. So that means that at the top, the kinetic energy is 1/2 of his mass times that velocity at the top squared. It gives you 2,292 joules. But the total energy at the top still has to be the same as it was before, 3840. So the missing part must be GPE. So if you calculate that, you get 1548 joules worth of GPE. And then we can find our height just by doing GPE over mg. So 1548 over 20 times 9.8, and it gives you 7.9 meters. So there's this height at the top of this path. Okay? Now, you certainly could have done that using projectiles, but since we're doing energy, it kind of made sense there. Okay, so that's that. Honestly, we probably could have done this one in honors. That one's not too bad. The next one gets a little bit more involved. Probably the next one would have been a very challenging honors problem. So let's run through it. All right, so in this next one, we've got a 5-kilogram ball. It's going to be dropped from 2 meters above a very large spring that's in its relaxed state. All right, and the spring has a spring constant of 40 newtons per meter. A wants to know how much the ball compresses the spring before it stops. So let's start there. All right, so the idea is, so here's your floor, all right? So you've got the spring. All right, and then you've got a ball that is 2 meters above it. Okay, then the ball is going to fall right before it hits the spring. It's going to be moving down. Okay, so we'll call this point A. We'll call this point B. Oh, shoot. Whatever. Okay. And then, so the idea is now the ball's moving. It's going to squish the spring until eventually the ball will stop at what we will call point C. All right. So let's make a quick note of the types of energy that the ball has at each point. So at point A, all of our energy is GPE. All right. At point B, well, this depends on what we determine, what we call a height of 0. So perhaps against my better judgment, I'm going to call this bottom point down here at point C a height of 0. Okay? Which means that if I call this distance x, the distance that the spring got squished, which is what we're trying to find, right? Then that means that at this point, at point B, my height is x, which means that I'm going to have some GPE up there, right? Okay. Now, the other option is you could call point B a height of 0, and then at point C, your height would have to be negative x. Okay. So either of those two choices work. Negative GPE always weirds me out, but it does work. Okay. So that means that up here, oh, I'm really unhappy with this. That means up here at point A, my height is 2 plus x, right? Okay, so that's my GPE. So my GPE down here is going to be 0. All right, so let's do GPE in red. Let's see, up at the top, there's no KE, there's no EPE. Down here at point B, we're going to have some KE, right? And then we haven't squished the spring any, so there's no EPE there at point B. But over here at point C, we do have some EPE, right? Okay, so that is that. And so the idea is, again, the only forces here are gravity and the spring. And so our total energy is constant. So let's do this, I guess. All right, so in order for, so we're trying to find x, right? So I think what I'm going to do is I'm going to focus on point A and point C. Sorry, I'm hesitating because I was solving this different than the way that I did it on my paper. All right, so here's why choice part B is not a good choice. At point B, we have 2 unknowns. We don't know what x is, and we don't know the velocity. Okay, so the reason I'm hesitating, we can find the velocity at point B. We know that it fell 2 meters, right? And so you can just do conservation of energy and figure out what the velocity is after it falls 2 meters. Okay. But I'm going to skip that. Let's just do this. Here's what we know. We know that the total energy at point A is equal to the total energy at point B. All right, so the total energy at A, well, that's gravitational potential energy at A. And at point C, oh, shoot. Sorry, just said I didn't want to do point B. Point C. So the total energy at A has to equal the total energy at C. So that means the GPE at point A, because all of our energy at A is GPE, that's got to equal the EPE at point C, right? Because at point C, the velocity is 0, the height is 0, so all of our energy is elastic potential energy. Okay, so here we go. The GPE at A is the mass times 9.8 times the height, which is stupid 2 plus x, right? And that's got to equal the elastic potential energy at point C, which is 1/2 times k, which was 40 times x squared. And solve it, right? So let's see, if we distribute, let's see, we're going to get 98 plus 49x equals 20x squared, which, if you solve it, gives you 20x squared minus 49x minus 98 equals 0. And so then we got to solve for our x. Okay, sorry about that. I realized I made a little mistake on my answer key here. So we got to solve this mess, right? So I would just use the quadratic formula. We've chosen x to be a positive value, right? Because of how we, like that yellow, or that pink rather. We chose x to be a positive value because we want this height to be bigger than 2, right? So we're going to do the quadratic formula here. Pick the positive value, and if you do that, your x turns out to be 3.75 meters. All right, so like I said, this is a very large spring. So the spring is going to get squashed 3.75 meters. Okay, so that is part A, 3.75 meters. Now, part B, this is the weird one. Part B says, what is the maximum speed the ball will reach? All right, and I'll be honest, the first time I saw a problem like this, I 100% got it wrong. All right, so let me clean this up for a little bit. All right, so here's the deal. So to do part B, here's the deal. So when the ball is falling, so while the ball is falling, before it hits the spring, the only force on it is gravity, right? All right. And so my knee-jerk reaction is to think, oh, well, the maximum velocity is going to be right here at point B when it hits the spring, right? Because as soon as it hits the spring, it's going to encounter some resistance. All right. But so what ends up happening is this. While the ball is falling, the acceleration is negative 9.8 meters a second squared. Okay. And remember, when it first hits the spring, if the spring is not displaced any, it doesn't exert any force. Okay. And so even if you squish it a little bit, then the spring is going to push up, but you're still going to have a net force that's down. All right? So we don't reach maximum speed until our acceleration is 0, right? And that occurs when our net force is 0. So what we need to do is we need to figure out how far we've squished the spring when the net force is 0. Okay, so let's do that. So let's erase all this nonsense here. So the idea is, here's the ball. Gravity is pulling it down with a force of 5 times 9.8. I think I said 19.6 a minute ago, sorry. So the force of gravity is negative 49 newtons. So the net force won't be 0 until the force of the spring is positive 49 newtons, right? So force of spring equals negative kx. So we've got 49 newtons equals negative 40 newtons per meter times x. So that's going to occur once the spring is squished. Let's just do this real quick since I made that mistake. 49 divided, oops, 49 divided by 40, so you get 1.225 meters, right? Okay. So how do we solve it? Well, here's what we're going to do. So we know that the total energy at point A has got to equal the total energy when you hit the maximum speed, right? So the total energy at A is the GPE at point A. That's got to equal the total energy at maximum, right? So let's see, at that point, we're going to have some GPE, because it will not have compressed all the way down to what we call the height of 0. So let's call that max, as in maximum velocity. So GP at maximum velocity plus kinetic energy at maximum velocity plus elastic potential energy at maximum velocity, right? So the GPE at A, that was the mass times the height, or times the acceleration of gravity times the height. Remember, our height was the original 2 meters plus how far we squished it, right? And that number was so the x that we found before was 3.75, right? Okay, so that's the GPE that we began with, right? And so now, let's see. We have squished the spring. We've squished the spring 1.225 meters, right? So uncompressed, our height is 3.75, but we're going to squish it down 1.225. So at this point now, we're at 5 times 9.8 times 3.75 minus 1.225 gives you, oh, that doesn't make any sense at all, 1.225, 3.75, there we go, 2.525, right? So that's our GPE plus our KE, which is 1/2 5 times V squared, plus our maximum elastic potential energy, which is 1/2 of K times this X that we found squared. All right, and solve it. All right, so I'm going to pause for a minute and figure this out. Okay, so if you simplify this, you get that your starting GPE is this, your ending GPE is this. You still are looking for this KE, but you still got this elastic potential energy, which is 30.0125 if you can't read my crappy writing. All right, so if you subtract the numbers from both sides, you get 128.0125 equals 1/2 times 5 times V squared. So divide both sides by the 2.5, and then take the square root, and you get 7.16 meters per second. All right, so there you go. All right. If you have questions on this, for sure we can ask. I'm going to stop there.